Thank you, everyone. I'll quickly share my screen. Can you confirm if you can see the first slide,
Yes,
please?
ma'am. It is visible.
Okay, because I can't see it on my screen here. Sorry, just give me a second.
It's visible, ma'am.
Yeah, all right. Yeah. Thank you so much. And thank you, Dr. Tanvi, for that generous introduction. Today, we are going to step into the unique and challenging world of space physiotherapy, exploring how the absence of gravity shapes human physiology in space and how we as healthcare professionals can contribute to optimizing astronauts' performance in space. Okay. All right. So, at the conclusion of this session, I trust you will leave with the understanding of the following key concepts. First, sorry. First, how the human body responds to the unique environment of microgravity with particular attention to musculoskeletal, cardiovascular, and the neurosensory systems. Now, these three systems are so finely tuned on Earth that they undergo remarkable changes in space. And following this, I will highlight the indispensable role of physiotherapy in long duration space missions in optimizing human performance in such an extreme environment, helping the astronauts not only to survive but thrive in space. So, the first question is, who is an astronaut? Um, So here I try to jot down, different aspects of an astronaut. So the astronaut is actually a product of science who is working in the field of space aviation, where he or she gets an opportunity to perform scientific experiments in space. So they know physics, understands gravity, understands the space environment. They are the explorer. They have solid engineering principle, foundations. They are psychologically fit. But the most important aspect for us, a physiotherapist, for us to know is that they are physically fit as well. All right. And um, the astronaut trainings, if you see, it is divided into different verticals, and one of the important thing is the physical fitness. So astronaut training is actually multidimensional, and it involves all of these, specialized area, each of them playing a very significant role in ensuring the success of a space mission. And we say that physical fitness and rehabilitation is one of them. So, just a first icebreaker for you all. How many space stations are currently orbiting Earth? Any guesses? You can simply unmute yourself or raise your hand to answer that.
Student
What do
can
you
raise
feel?
the hand. We will share the mic with you. If anybody knows the answer, simply raise your hand. I guess nobody is there to answer, ma'am.
Okay, that's all right. So currently there are two space stations which are orbiting Earth. One is the International Space Station where Shooks from India recently went, and another one is the Chinese space station. So yes, they have their own space station, and I believe that India with the Gaganyaan mission is planning to launch their own space station. So hopefully we'll see that in future. And my answer would be changing very soon for this particular question. All right. So from here, we move on to our first module of today's webinar, that is the space physiology. Now, space is a microgravity environment, which means that some of the mechanical forces on the body that we are used to on Earth, they are either absent or reduced in space, resulting in changes in various systems of the body. And that's what I am going to discuss today. So let's start with the first system, that is the musculoskeletal system. It comprises of bones and muscles. Coming to the bones and muscles, so they are formed as a result of first the 1G, that is the gravitational environment of Earth, and second, the mechanical forces which are exerted on the body. Okay, so the major bones, they are primarily involved in counteracting the force of gravity, are your lumbar vertebrae, the pelvic girdle here, the femur, tibia, and your calcaneus. So they are the primarily bones which are counteracting the force of gravity here on Earth. So now what happens on Earth is when the bones are stressed by gravity, the bone breakdown and formation equals. Hence, there is no apparent bone loss in a healthy individual. Okay. But in microgravity, there is no gravitational stress on the bones. So the bone breakdown continues, but the formation reduces. And this results in bone loss in astronauts. All right. Next, we will see the muscles. So similarly, the lower limb muscles are the primarily anti-gravity muscles or the skeletal muscles that counteracts the force of gravity on Earth. On Earth, the muscles are stressed continuously by the gravity, so the protein breakdown and the protein synthesis equals. Hence, we do not see any muscle loss or atrophy in an apparently healthy individual. Whereas in microgravity, because of absence or reduction in the gravity, the protein breakdown continues, but the synthesis reduces. And this results into muscle atrophy or muscle loss in astronauts. So it is very well documented that because of the absence of the gravity constraints, astronauts can lose up to around 2% of their bone mineral density per month, which is way higher than what we see in an osteoporotic individual on Earth. And as you can see here, in case of the muscles, they lose around 11% in the back muscles, 12 in the thigh muscles, and a lot, that is around 20% in the calf muscles. So all this changes combinedly results into muscle atrophy, decrease in muscle strength, loss of muscular stamina and contractile endurance, increased fatigability, pain, and injuries in astronauts when we are talking about the musculoskeletal system. All right. So next we will be moving on to the cardiovascular system. So most of us do know that the cardiovascular system primarily consists of the pulmonary circuit and the systemic circuit. Okay, so the deoxygenated blood from the upper body, the lower body, the brain, everything, it goes towards the right side of the heart. From the right side of the heart, it goes to the lungs. From the lungs, it gets oxygen and called as the oxygenated blood, which comes to the left side of the heart. And from there, it is getting distributed to different parts of the body. And we all know that calf muscles plays an important role to push blood against gravity on Earth. All right. Let us have a little bit discussion over the initial effects of standing on circulation. So when we stand on Earth, okay, the blood will start pooling into the lower part of the body because of gravity. Now, if that happens, so the venous return to the heart should be reducing. If venous return reduces, there would be reduction in the blood pressure, reduction in the blood flow to the brain. And if that persists, there would be lack of oxygen to the brain, leading to dizziness, impaired consciousness, or impaired vision, and so on. But this does not happen on day-to-day basis when we talk about an apparently healthy individuals, or when we talk about you all. So what happens is, as soon as we stand, there are some physiological changes that are happening in the body. So there would be increased heart rate that partially restores the blood pressure. There would be constriction of the veins or vasoconstriction of the arteries that to, in turns to try restore the blood pressure, and definitely the calf muscles plays a major role into it. And these changes actually helps to restore the blood flow and the oxygen to the brain, and thus we do not see all those changes which are expected in case these changes do not happen. Now let's see what happens in microgravity conditions. So I would first like you to just have a look at the picture on the right side of the screen. Where can anyone identify? Um, okay, I would not say the name of the astronaut, but at least from which country she is and what is very special about this astronaut. Anyone who is joining from their laptop, simply unmute and you can answer it. Is there anyone, Dr. Tanvi, would like to answer? Okay, if not, the second question, I will answer that. The second question, do you see any changes in her when, under the 1G, that is the Earth, and micro G in space? Do you see any changes in her?
Any of the student can answer. Beta, raise your hand.
And no pressure, there is no right and wrong answer here. It's just your observation.
I guess, ma'am, they are trying to understand the things, so you can continue.
I completely, yeah. I completely understand that. It just, do you observe any difference, or apart from the uniform, what they are wearing? So do you see any difference in them? Yeah.
Hello.
Yes,
Hello there.
Now we can see the puffiness on the face that probably is due to fluid retention.
Yes, perfect. Yes. So that is what happens in microgravity conditions. Okay, so I'll just give a little bit about this astronaut. So she is the Chinese taikonaut Wang Yaping. She is the first Chinese woman to walk in space, that is to do the spacewalk, and that is what is the specialty regarding her. All right. So we did see about the blood flow, what happens is, right, and the role of calf muscles. What I would like to highlight here is that there's also a liter and a half of fluid in the lower part of the human body, which is outside the circulatory system. Okay, and what is interesting to know here is that gravity keeps it there. So when astronauts enter microgravity, this fluid flows up into their chest and head, and correctly said that you can see the puffiness in the face. So this is called as the puffy face and chicken leg syndrome. So then the lower body actually gets a bit, shrinking up compared to what it is there on the Earth. So over the period of time, now what happens is there are significant changes which are being seen in the astronauts other than puffiness and chicken legs. So there is reduction in the circulatory blood volume, reduction in heart size, reduction in aerobic capacity, and post-flight orthostatic intolerance. So I'm not sure if any one of you have seen the videos or the photos when the astronauts land back on Earth. So it is similar to the orthostatic intolerance, what we usually see in our patients when they stand up. This usually happens in astronauts once they are back to the Earth's gravity. Okay. And here comes our last system, which is the neurosensory system. The neurosensory system comprises of the three systems: the visual system, somatosensory system, and the vestibular system. Okay. Now, the visual system, it includes your eyes, the connecting pathway, and the visual cortex, which is required for your visual perception, that is receiving, processing, and interpreting the visual information to build a representation of the visual environment. Coming to the somatosensory system here, so it is the part of the sensory system which is concerned with the perception of touch, pressure, pain, temperature, position, movement, vibration, all of these sensations which arises from the muscles, joints, skin, or fascia. And lastly, the vestibular system. So it is consist of the three semicircular canals here and the otolith organs here, the saccule and the ventricle. Now, the main purpose of the vestibular system is to create a stable platform for all of us. So when we are on earth, we can orient ourselves to the vertical. That means if you're sitting or if you're standing, you can tell me where is up and where is down, and you can move on smoothly. But this is something lacking in space. So in space, the astronauts, with the help of their vestibular system, cannot detect what is up and down there. I would simply want to highlight a little bit more about the vestibular system here. So the vestibular system actually counteracts the linear acceleration system and the angular acceleration. Okay, so the linear acceleration sensing system, it sends message to the brain as how the head is translated or positioned with relation to the force of gravity. Okay, so it contains two tiny sacs filled with fluid, the saccule and the ventricle, which is lined along the inner surface of the hair cells. The angular accelerating system, it comprises of the three semicircular canals, and this system detects the angular acceleration through the inertial movement of the liquid, that is the endolymph, within each canal. So all of these three systems, they send input to the brain or the central nervous system, where what happens is the complex interactions will take place, and this results into appropriate body posture and movement. Okay, now here we are going to talk a little bit more about the otoliths. How actually, when I say that, it sends the input through gravity. So when we are on Earth and the head is not moved, they are not stimulated. Okay. When the head is tilted because of the force of gravity, these crystals are bent down. Now, when they are bent down, that's where the signal goes to the brain that yes, the head is tilted. Okay. Now, if they are not stimulated, that means they are not going to send any input to the brain. And the second thing is the vestibulo-ocular reflex, which is the gaze stabilizing reflex. Now, the sensory signals, now this is the reflex where the sensory signals that encodes the head movements, okay, they are transformed into the motor commands, which will generate the compensatory eye movement in the opposite direction of the head, and thus ensures that the vision is stable. So there is a lot that goes on when we talk about our posture or the balance or the equilibrium of the body. All right, next just we'll see what happens in microgravity. So coming to the visual system, we already saw about the fluid shift in microgravity. Now, because of the fluid shift, it results into the pressure around the optic nerve, resulting into its compression, flattening of the back of the eyeball, optic disc swelling, and this all results into the visual impairment. There is optic disc edema and the globe flattening. Somatosensory system. Now, astronauts, they are always floating or using their upper limbs for moving around, unlike on Earth where we use our lower limbs. So there is little to no input from the lower limbs that results into degradation into these proprioceptive function and inaccurate external spatial map. And coming finally to the vestibular system. So when the head is tilted in space, the joint and the muscle position sense, it gives input to the brain that yes, the head is tilted. If the eyes are open, the visual system is also going to send the same input to the brain that yes, the head is tilted. Whereas because of the absence of this gravity stimulus or insufficient gravity stimulus, the otolith organs are not stimulated. So what happens now is the brain starts to receive mixed input and it gets confused, right? So once it gets start confused, it's try to understand what is happening. And over the period of time, what happens is this otolith interpretation of tilt is inappropriate. So therefore, there's a theory which says that it is possible during adaptation to the weightlessness or microgravity environment, the central nervous system reinterprets all of these otolith signals to indicate translation instead of a tilt. And this is called as the otolith tilt translation reinterpretation. Coming to the vestibulo-ocular reflex, it also becomes less efficient as the duration of stay in the space increases. There are evidences which also indicates that the spaceflight environment induces adverse effects on the brain, including the intracranial fluid shift. There is changes in the gray matter, white matter. There are adaptive neural effects like sensory reweighing and neural compensation, right? On all these adaptations in the neurosensory system, it results into spaceflight associated neuroocular syndrome, which is a medical condition that affects the astronauts during long duration spaceflight mission. And that will give you a combination of symptoms like blurred vision, optic disc edema, glow flattening, refractive changes, altered postural control, and so on. So overall, if we see the astronauts suffer with space motion sickness almost 90% or 95%. Astronauts experiences space motion sickness as soon as they enter the space. Then the SANS, just now I spoke about it, the altered postural control, balance or disequilibrium, gait instability upon returning to Earth, and problems in eye-hand coordination. So if I have to conclude all these systems, we all will agree, me saying that they are being deconditioned or they are not being functioning properly. Okay, so the profound multi-system change takes place in human body. They are seen as it adapts to a new environment of microgravity. Now, this adaptation is frequently referred as deconditioning, and to the best of mine, this was very much highlighted when the stay of NASA astronaut Sunita Williams was extended, that she's deconditioning, declining in health, and so on. But we have to understand as in healthcare professionals that these changes are being called deconditioning or unfavorable because the changes are unfavorable for the life on Earth's gravitational environment rather than the actual microgravity environment. So, in general, the deconditioning are the physiological adaptations to microgravity environment or weightlessness, and they are not a significant problem. Yes, they are not a significant problems as long as the astronauts remains in space. The physiological problems or the deconditioning, what we highlight, arises when the astronauts returns back to Earth's gravity. And we all know they are not going to stay there forever, as if now, according to the space policy, they are going to come back to the Earth's gravitational environment. And that's where our role as physiotherapist emerges in supporting the astronauts so that the space mission is successful. Now, each space mission is divided into 3 phases: pre-flight, in-flight, and post-flight. Okay. Pre-flight is when an astronaut is selected for a space mission and until they fly in space. In-flight, their entire duration of stay in space, and post-flight is once they land back on Earth. Pre-flight, all the candidates, they meet the basic physical selection criteria. Okay, that includes their height, weight, and there is a individually created assessment for specific agencies. So like if we talk about NASA, they have their own assessment protocol. If we talk about ESA, they have their own assessment protocol, and now ISRO must be having its own as well. So a detailed examination that comprises of body composition, muscle flexibility, muscle strength, including the hand grip strength, power, core muscle endurance, postural stability, cardiovascular capacity. This all is being collected. And following by this, the data would be matched with the standard criteria of a particular space agency. And then the exercise protocol is customized using the FIT principle. So pre-flight, which begins once they are selected, it consists of mix of supervised and unsupervised exercise sessions. The supervised sessions consist of typical gym exercises, as you can see here in the video, but the specific focus is on the development and implementation of individualized International Space Station or in-flight exercise protocol. So on a regular basis, at the best, I can say it's on a monthly basis, the astronauts, they are requested to provide their training data, including the type of exercises they are doing, the training time, intensity, and their personal feedback as well. So once this data has been collected in conjunction with the standardized pre-flight assessment, what is being done, then the physiotherapist will use this data to tailor the in-flight exercise protocol. Now, this period is also crucial for us to build the trusting relationship between the astronaut and the physio. This will ensure the compliance between these two. Now, in the video you have seen, he's doing all those gym-based exercises, stretching, strengthening, aerobic training. I would like to highlight here that yoga is something which is primarily being practiced by the Indian astronauts. Recently, Shooks has practiced it during his flight to International Space Station. And Rakesh Sharma, who was the first Indian astronaut to fly to space, he was the first one to practice yoga in space, and that's why he's fondly also called as Antariksha Yogi. Apart from this gym-based exercises, here you can see in the pictures, they are doing some other bits as well. So they are being trained for their hand exercises, the glove fittings, the hypobaric chambers to identify if the oxygen levels drops in themselves. Here you can see the anti-gravity treadmill training, the VR training or the XR training. But the most important thing, apart from these bits, are the training with replicas of station-specific equipment. So here on Earth, they have the luxury of meeting all of us, having that setup, gym setup, having access to different equipments. But when we talk about space, there is a limited space and time for exercises. So they must be trained how to use a particular equipment for given set of exercises. Now, one of the equipment which is in the NASA module of International Space Station is the ARED device, this device, which is the Advanced Resistive Exercise Device. It is slightly different than the squat rack in the local gym, but has similar functions like they can do the squats, deadlifts, bench press, shoulder press, etc. So all those similar exercises what people do in the gym. But the difference is here because there is weightlessness. So this equipment is been embedded with 2 canisters, that's what he's showing there, which has vacuum. So the astronauts is actually pulling against the vacuum. Once the protocol has been given, which exercises, how many repetitions, how many sets, everything has been provided. So what the astronauts have to do is they first we introduce them, what are the different parts, how do we adjust the load here, how do we adjust the equipment, the same set of equipment for different exercises, whether it is upper limb or lower limb, right? So once that adjustment has been done, as you can see here in the video, he's trying to adjust the bar to the given height so then he can start doing the exercises. Then they stand on this yellow platform. So the black platform where he is standing right now is not there in space, or I would say ISS. So they stand on this yellow platform and then do the different set of exercises, which has been advised for them for a particular session. So this is only one which I'm covering here in the pre-flight. We'll see the other two pieces of equipment once we go to the in-flight session. Now, the next icebreaker. Anyone can guess how long are astronauts quarantined before flying to space? Any guesses? So it's like once the pre-flight phase is completed, then the astronauts are being quarantined. After the quarantine, then they will be flying to space. So any guesses how many days or weeks they would be quarantined minimum before flying to space? Um, I can hear some sounds, but I can't make out what you're saying. Sorry about that. I'm not sure if anyone is typing in the chat. Um, is it okay if that's all right? So it's minimum 14 days of quarantine. What they undergo minimum. If during the quarantine period, for any reason, the launch is delayed, say by 2 days, 4 days, or so on, which actually happened with Shirks, then the quarantine continues. But if the launch is postponed for indefinite period of time, then the astronauts are being released from the quarantine and then they will be re-quarantined again for 14 days before actually flying to space. All right. So here comes our in-flight phase now. So the in-flight phase is divided into three phases for a long duration flight. The first phase is the adaptation phase, which is the day when they reach this phase up to the 20 days. This phase is important to familiarize the crew members with the ISS exercise hardware, to the new environment of microgravity and how to use it in microgravity conditions, adapt doing those exercises in microgravity condition as well. Phase two is the main phase where they exercise full-fledged to prevent the effects of microgravity. And phase three is preparing them for re-entry. Those are the final 15 to 30 days. So we prepare the crew member for rigorous re-entry and potential of nominal landing scenarios. Here the goals are to maintain good health conditions and high work capacity of the crew member, to mitigate the effects of microgravity and save the coordination abilities that will allow them to maintain vertical position, to walk or run in case of emergency landing after returning to Earth. Okay, so there are three pieces of equipment in the NASA module of International Space Station. The first one is the CVIS, that is the cycle ergometer vibration, isolation, and stabilization, similar to the stationary bike, which is there in our gyms. But funniest part is that there is no seat needed for the astronaut here to sit and do the cycling. Yeah. So they put on the harness so that they don't float away. And then they do the cycling according to the prescription. So, um, for example, if I have to give you the protocols for CVIS are based on oxygen consumption, that is the VO2 max, and there could be a graded cycle ergometer test that could be used for it. Steady state protocol is the simplest example what I can do here. So the astronauts performed approximately, say, 80% of the pre-flight VO2 max when they are on in space. The next one is the Colbert, which is the combined operational load bearing external resistance treadmill, similar to the treadmill what we have here on Earth. Little bit difference that it provides a motorized speed up to 20.4 kilometers per hour. Again, they wear a harness, and if you can see a tethering cord here, now this tethering cord here is used to vary the loads for each session or according to the given protocol. Now, the treadmill protocol intensity, again, this is also increased throughout the mission by modifying the running speed and the interval duration. And the last one is the ARED, which we have seen into the pre-flight. It provides load from 2.2 to 272 kilograms. So that is how the ARED has actually replace the previous equipment IRED because it could give you more variability and more different set of exercises could be done. Now, after this in-flight phase, here comes the post-flight once they land back on Earth. It is again divided into three phases. First 2 days, we give the astronaut time to adjust back now to the gravity or the gravitational environment of Earth, then back to function and back to Earth. So the goals here for the post-flight assessment is to prevent the long and short-term painful conditions from developing, addressing any mission-induced physical health problems, and returning them to their pre-flight condition without risking the development of pain. Now here you can see in the assessment, this is a set of battery, the functional task test, what NASA usually uses. So it comprises of different tests. Here you can see is walking with heel to toe pattern with the eyes closed, right? So this is one of the functional task tests or one of the test batteries which has been developed, but there are others as well. And this is to evaluate the post-flight functional performance as well as the related physiological changes in it. And we're going to shortly do this if the volunteer is ready and see what happens in here. Okay. So I will stop sharing my screen now. And if we can have the model, please. Is the volunteer there? Yeah, so I've requested for 3 volunteers, one to be the model and 2 other persons to assist.
Khushi Soni, Anjali Sharma, come to one Abhishek Jha, Devesh, Dr. Bhavna.
Dr. Tanvi, if I can know who would be the model?
Yes, ma'am. Varsha will be, Devesh will be the model, Devesh.
Divesh, all right. Divesh, can I have a quick chat with you if you don't mind, please?
Devesh,
Until the
come,
setup is done.
take your mic. Saurav. Abhishek Jha, assist Devesh.
Hello.
Hi, Divesh. Thank you for volunteering, first of all. Just few questions, if you don't mind me asking you before we started. Okay. First thing, I can call you Devesh, right? Sorry, your voice is breaking. Okay. Second thing, where are you from?
I'm from Delhi.
No, I'm not able to get to you.
I'm from Delhi NCR.
Are you from Delhi? Sorry. Okay, I'll modify my question, what I wanted to ask you. Which planet you are from?
I'm from
From Earth. Okay. All right. And have you ever left Earth before?
No.
Are you sure about that?
Yeah.
Okay. And can we consider you as an apparently healthy individual?
Yes.
All right. Thanks for that. Okay. So what I'll do is I'm going to give you some instructions, okay? And I want others to observe, just observe, what Devesh is doing. And if at the end, we are just going to discuss if anyone would like to. All right. Devesh, I hope you will be safe. Okay. There should be no falls, to be honest. But and at any point of time, if you feel you are not safe, I'm happy for you to terminate it. Yeah. So you don't have to continue doing it if you are not feeling good. All right. Okay. So if we can hand over the mic and then we can simply start with it. Um, yeah. I can see you very well. Okay. So what we are gonna do, so we're gonna do two different stuff. Okay. I'm just trying to do a simplest simulation, what I can. Thank you for adjusting the camera. I would definitely would like to see Divesh. Divesh, if the mat can be just placed aside for the first task, and then I would prefer you put it in.
Yeah.
Yeah. All right. So Divesh, you stand at the one end. Perfect. Okay. Uh, along the path that you would like to walk. So I think you will have to turn. Yes, thank you. All right. Look straight ahead. Cross your arms across your chest, please. And can you do 10 heel to toe walk? So try and touch your heel of the foot to the toes or tandem walk. No, you have to, no, not on the, no. You have to do a tandem walk. Yes. Yeah. With your hands crossed across the chest, please. Can you cross your arms across the chest, please? Yeah. Can you do 10 heel to toe walk? Yeah. Keep doing it. You don't have to look at the screen. Just keep walking for 10 times. Yeah.
आओ सर आप यहीं बैठो
Perfect. Okay. Thank you. Can you just turn and do one more time so then the participants can observe you? Perfect. All right. Now I would request the others to please help Divesh to put on the wrist and arm weights or the weighted jacket. And if the chair is there, Divesh, you can sit on the chair. And then I would request the mat also to be placed in front of Divesh, please. Yeah, so put the chair at one end where you are. Perfect. You can sit there, Divesh, and I believe others can help you to wear the weighted jacket and ankle and wrist weights, please. Let me know when you guys are done with this setup. Okay. If you can please place the mat in front of Divesh the same way how he has walked before. Divesh, you keep seated. The others can help, please. Okay. All right. Now, if any one of you who is standing, Divesh, are you okay? Yes, okay. I can see that thumbs up. Perfect. So what I want, okay, first instruction would be for you, Divesh. What is going to happen is now the friends of yours are going to rotate you in the chair, okay? And then say we will do it around for 10 seconds or 10 to 15 seconds, okay? After that, you have to stand up, cross your arms, and walk same way, the tandem walking on the mat, please. All right. So I can see three other volunteers being there. Amongst you three, can one be please there with Divesh to rotate when I say that? And the other two volunteers, please can you be on the either sides of the mat? Okay, so the other two volunteers who are standing on the either side of the mat, be with Divesh when he's doing the tandem walk. All right. Okay, guys, he has said that he has never been to space before and he is an apparently healthy individual. Now, the one I can see standing behind Divesh, please can you rotate him for 15 seconds and we are going to count it faster. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and stop. Divesh, please stand up, shut your eyes, cross your arms, and walk. Walk, walk, tandem walking. Please start immediately. Oh no. Okay, walk, 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 10, 10. Come on. Okay. All right. There we go. Thank you so much, guys. Thank you so much. You can have a seat, Divesh. We will talk to you in the meantime. Anyone would like to share what they observed? Sorry, I can't hear again. If you can bring the mic closer, I think it would be easier.
Disturb balance.
Oh, he lost balance. Yes. Anything else? Anyone would like to share?
Body.
Sorry, can you repeat that?
Shivering was there in his body.
Mm-hmm. Yeah.
And it was
Yes. All right.
all
Is there any?
nervous system was disturbed.
I think it is echoing a little bit. I'm not sure why.
Eyes were
Eyes closed. Yeah, yeah. Or more challenging. Yes. Okay. Can you pass it on to Divesh just to share what he felt?
And lack of balance, no visual cues, so it is hard to walk.
It was
When
difficult for you, right? Yes. So now I would just like you all to think for a few moments. He said he never left Earth. He said he's an apparently healthy individual, okay? But just within 15, 20 seconds, we did that setup and he lost his balance. He was struggling to walk. He needed help, right? So let me explain what I tried to do with him. First thing, I requested him to wear all those weights, okay? So now once the astronauts come back on Earth, they feel their bodies are very heavy because now because of the gravity, they can feel their body weight. And they explain it is like when they are re-entering, it feels like a sumo wrestler is sitting on them. So even lifting a small water bottle is a task for them. Okay. Second thing, what I did was to put a mat that was simply to alter his somatosensory system from the legs, the inputs which he's receiving. So we are actually trained on Earth to walk on hard surface most of the time. Okay. And the third thing was to rotate him is to play with the vestibular system. I shut again because we don't have the distortion glasses. Otherwise, we have used that. But with eyes shut again, I was trying to conflict the visual input. So now with this simplest simulation, what I want to demonstrate is within 15 to 20 seconds, if this can happen to an apparently healthy individual who's been constantly under, the gravitational force doing all things normally, just imagine even within 1 week, if we spent in space, what would happen to our body? Does that make sense?
Yes.
Yeah. Okay. And I hope, Devesh, you are okay now. Thank you so much. And I'll restart my screen and you guys can take place here. Thank you so much for volunteering and supporting with this activity. Okay. Screen two. Can we start after this? So that was our engagement activity for today, just to give you a little bit, how it feels, how it looks when we see the astronauts. Okay, so this is the reason why post-flight rehab is required, right? So during the daily 2 hour session, the first hour is dedicated to physiotherapy, addressing any specific conditions if they are suffering from. So the first week, the exercises, they are performed in swimming pool in coordination with the gym sessions. Now, why swimming pool? Because the feeling of neutral buoyancy in water is perceived as comfortable by the astronauts, reminding them the absence of their body weight in microgravity. Now, as the crew member progresses, the gym time versus the pool time increases, and more exercise then would be performed in the gym because our primary goal is to get them back to shape, or I would say to their pre-flight fitness level. Okay. So initially, the program focuses on basic ambulation, cardiovascular endurance, strength, balance, flexibility, and proprioception. And later, more active conditioning regimes are being added, like adding the high intensity aerobic exercises, strength training, introducing power type exercises like jumping, medicine ball exercises, and then more and more complex movements for balance, agility, coordination, they all are being progressively added. So mostly it is a 45 days of rehab program, plus and minus. Why I say that is there are evidences that astronaut may take up longer time than 45 days, depending upon if they have an additional injuries. So after that, what happens is we train them, and I tried to jot down, a little bit how the schedule looks like in terms of the exercises, what we do. So first, on the day of landing to say 21 days, the intensity level would be progressively increased without evoking any strong physical effects. And from 21 to 45 days, then we try and implement the pre-flight exercise program. Now, after this, they are continued to have that post-flight rehab until the assessment or the examination reveals that they have regained the pre-flight fitness level. And then after that, we release them from this formal post-flight rehab, but we encourage them to participate in the maintenance program. So it doesn't stop in there. So that summarizes what happens to an astronaut in the microgravity environment and how we as in healthcare in different stages of the space mission, pre-flight, in-flight, or post-flight, are integral to support the space mission by maintaining the astronaut health. So for conclusion, I would like you to listen to this astronaut before I say my bits, because I am a physiotherapist and you guys are physiotherapists, and we all are advocate of exercises. We say they are the best way to keep us healthy. So let us hear what he's saying.
One thing to remember is you want to enter your space flight in as best shape as possible. It's hard to make up for a lack of exercise while you're in space, but it is much easier to be able to maintain where you are and maybe get a little better if you enter the flight, if you launch in pretty good physical condition. For now, the best way to stay healthy in a zero gravity environment is to exercise.
Yeah. So even evidences says that the best way to stay healthy in microgravity environment is through exercises. So just to summarize everything we have seen today, first thing, microgravity, yes, it triggers multi-system decline, but it is predictable, okay? Second, exercises are the primary and highly effective mitigation strategies, which is used to offset the spaceflight-induced multi-system deconditioning. And physiotherapy is not optional, it is mission critical, okay? The third thing which I would like to highlight here is that India is taking its first human steps into orbit with Gaganyaan mission. And Gaganyaan's success will depend on how well we prepare and protect the only thing that cannot be replaced in space, that is the human body or the astronaut. So my closing message is very simple. Microgravity will always try to break the astronaut. It's your job, it's our job as physiotherapists to make sure that astronaut breaks the microgravity first. Gaganyaan is India's leap into space, and let us make Indian physiotherapy to leap with it. Yeah, thank you so much for your time and attention. It's been an honor to be providing an overview of this important topic and rarely discussed topic. As we look into the future of space exploration, I encourage you to stay engaged with the latest research and advancement in this field. Yeah, thank you so much. And if there are any questions, I'm happy to take them.